Hi everybody, Morgan here, talking about gases once again. AP outline, page 8 of 16, and you're looking at something very familiar to you, our good friend, the roadmap. And hopefully you're remembering that the balanced chemical equation can be used to convert between molecules of A and molecules of B, or moles of A and moles of B. And last year we spent a lot of time calling that the mole ratio. And we're good with all of these. And today we add a couple of roads to it. Coming off of moles of A, we're going to put gas volume of A, and coming off of moles of B, gas volume of B. Now we'd had liquid volume here before just for doing, like density problems. Okay, but these are gas volumes. And we can use V equals nRT over P for doing those conversions. All right? So these are stoichiometry problems with an extra step thrown in. So we look at this and it asks us how many liters of carbon dioxide will form at STP from the reaction of 50 grams of calcium carbonate with excess hydrochloric acid. I need a chemical reaction. CaCO3, okay, plus my HCl's to give me CO2 and H2O and CaCl2. We'll throw a 2 in front of that. The CO2 and the H2O, they actually come from H2CO3 breaking down. So it's a double replacement, and then there's a decomposition involved. Okay? So where am I? I'm on the mass of A, 50 grams of calcium carbonate. I'm going to go mass A to moles of A, then I'll go moles of A to moles of B, out to gas volume of B. So 50.0 grams CaCO3 times. Now, I got to tell you, this is really one of my favorite compounds for math problems because it turns out its molar mass is 100.09 grams of CaCO3 for 1 mole of CaCO3. So the math gets really easy, okay? And since we're only 3 sig figs over here, I don't really even care about the 0.09. It's a 1-to-1 ratio. For the calcium carbonate to the carbon dioxide. Now, when I look at this, just off the top of my head, I can tell it's 0.500 moles of CO2. Because that cancels and that cancels. Now, I can do 2 things here. I can do a PV equal nRT, okay? But it's at STP. So my other possibility is just to say 0.500 moles times 22.4 liters per mole. The moles cancels, and I get 11.2 liters of CO2. Now, let's be honest, they don't turn out that easy most of the time. Most of them don't happen at STP, okay? But that does work for this one. Okay, now, much more straightforward, reasonable style question here. Oxygen gas is prepared by the decomposition of KClO3. If you need 1 liter of oxygen gas, how much KClO3 do you need to start with at STP? So our reaction is KClO3 decomposing. That's going to give you KCl and O2. That balances 2, 2, and 3. All right? Now, 1 liter is what I'm looking for. Again, it's at STP. So, NPV equals nRT. N is equal to PV over RT. And in this case, 1.00 ATM. Then that's the 1.00 liter I'm looking for. R is 0.0821 liter atmosphere per mole K. And the temperature at STP is 273 K. Atmospheres, liters, and Kelvin cancel. And this came out to be 0.446 moles of O2. Now, what I'm going to do at this point, okay, you know what, I'm sorry, 0.0446. 0.0446. Now, I'm back onto the roadmap again, and this will look very familiar to you, where I say 2 moles of KClO3 for 3 moles of O2. Moles of O2 is going to cancel. 1 mole of KClO3, and I added it up as 122.55 grams KClO3. All right, you might get a slightly different number depending on which periodic table you were looking at. 3.64 grams KClO3. Okay, so get that lined up for you there. There we go. All right, pretty straightforward types of problems. Okay, I'd like you to try the next page on your own, see how you can do. Okay, and then tune back in for the next video just to check and see how that one turned out. Okay, this is Morgan signing off.